All right, so welcome everyone. So it's my great pleasure to introduce Priyank Jaini. So Priyank is actually an alumnus from Waterloo. So he did, well, he first started as an undergrad doing an exchange program here. And as he was reminding me earlier today, when he first came, he didn't like our winter and promised himself that would be it.
Yeah.
But then he actually liked Waterloo gradually, came back for a PhD. I was fortunate enough with Yang to be his co-supervisor. So he worked with Yang and I on various problems in machine learning. And Priyank has worked on a number of problems that are very interesting. And today he'll tell us, I guess he'll give us a brief overview of this variety of problems, but his background is statistics, and you'll see that even though deep learning often, has some roots in a way that are very intuitive and heuristics, he likes the more fundamental part of it, and he'll show us, I guess, some of the advances that he has developed that have, good roots in principal techniques. Today, he is a research scientist at Google Brain. So he spent some time here in Waterloo, sometimes in Toronto as well. And yeah, so he's doing some really exciting stuff. And I'd like to invite anyone afterwards, to ask him some questions about whether it's research or what is life like to be a research scientist at Google. So in any case, yeah, after the talk, feel free to stick around and talk with Priyank. So in any case, he's here to tell us about all the good things.
Thank you.
Okay,
thank you
so I guess, yeah, without any further ado, let's welcome Priyank. And
thank you, Pastor. Thank you for the introduction. Yeah, thank you everyone for joining the talk. I would say in some ways it is homecoming, but I've always been in Waterloo, so it's great to be here on the opposite side giving this talk. I'm really excited and also a bit nervous about it. So I think I hope that you'd like it. So today what I'll talk about is a bit of our work from the previous years on how to exploit symmetries, I call it here, but mostly it's around how to incorporate inductive biases in generative modeling and how to make generative models more flexible, unconstrained, expressive, and efficient. Also, before I begin, those who are joining through the Zoom call, because I can't see you, if you have any questions, just ask the question directly so I know that I have to stop and take the question because I can't see anybody on the screen. So most of this work that I'll talk about today was done when I was a postdoc at the University of Amsterdam. And there are two different projects that I will touch on briefly, but both of them would have a common thread of how we can incorporate symmetries and equivariances into generative modeling paradigms. And so before I even begin, I would set the stage with how I think about research problems and how I've been thinking about research for the past couple of years. But a lot of work that I would talk about today is in collaboration with these awesome people. So Max Welling and Bernd Ensing are both professors at the University of Amsterdam. One work that I talk about was done with Ferry Hooft, who's a PhD student with Bernd. And the real stars are Lars and Yuanqi. Lars is a master's student now converting into a PhD, and Yuanqi was an undergrad when he did this work today that I'm going to present, and now he's going to be a PhD student. So these two are the real stars of the work that I'm going to talk about today. I just get to take the curtain call. So how I think about machine learning, and maybe it's not really a textbook definition, but I think the general recipe of learning consists of two ingredients. One is inductive bias, which is what we know about the world, and the other is data. And it's really how we combine these two ingredients that leads to different learning paradigms. And so there is this modeling spectrum, wherein on one side you have what I call, I just want to have, I can't get a pointer, I guess. Okay, that's a pity. Okay, I will try to explain because I can't get the pointer on. Okay. Oh, I mean, it's fine. I will explain. Where's the pointer? Is somewhere. Okay, that's fine. So yeah, on one end of the spectrum where I've written them as discriminative models, but what I really mean is deep learning models for classification here are models that just let the data speak. So you have lots of data in those domains and you can train your models. The advantage is that these models have been useful in quite a lot of domains, but they are also limited. So you train on a domain and you can only apply these models on that domain. They don't have any cross-domain application. On the other end of the spectrum, where you can have a lot of inductive bias, are what I would call generative models. So for example, one of them would be simulators, which is simulating the data generated process itself. The advantages of these models are that you can incorporate a lot of inductive biases into it. So you know the physical properties of the world or the application that you have in mind, and then you can create a simulator out of it. The advantage then is that it generalizes well. So if something changes, but the overall properties are the same, it would generalize well to that domain. So as I was saying, that discriminative learning is sort of in the way that you let the data speak, and how it works is that you have some raw inputs, you send it to this pipeline of a neural network that you have created, and it generates certain predictions or semantics or whatever class properties that you're interested in. And this has been hugely successful in these three domains, at least that I've written here, which is, one is image understanding, whether it goes for segmentation or recognition or so on. Speech recognition and machine translation are also two domains that have seen a lot of this kind of work being highly successful there. And on the other hand of the spectrum are what are generative models or forward models. So in that space, I would put simulators, graphical models, or more probabilistic programs, etc., as these kinds of models. So for example, one of these would be what I show here on of two galaxies colliding. And to create a model for this, I actually can create a model without any parameters or as low as 2 parameters, because I know the physics of the problem. So I can create a simulator that can then create this data generation process of what happens when two galaxies collide, and I can get this simulation out. Or you can do sort of like weather prediction, where you know how the system, it's a stochastic system, but you can define it through certain stochastic differential equation and then sort of try to predict what would happen over time. And then you can predict rainfall or what the temperature would be. You can also predict drought situations using these models. Or even sort of this, like how a molecule would evolve and how the electrons around the molecule would evolve over time, etc. So these all you can simulate because you know a lot about the inductive biases, or you know about the physics of the problem, and you can incorporate in data. I put one more thing example here, which is image generation. Honestly, this would fall into a paradigm that involves both generative modeling and discriminative modeling, but I put them here just because earlier when I used to give a talk, I used to say that one goal of mine is to say that I imagine something that I haven't seen. For example, let's say a pink gorilla on a moon with a clown hat juggling balls, right? And I can think about it, but can I make a computer think about it? And 2 years ago, I thought that, okay, this was a challenge that I would love to work on. With these models that have come off in the last month, like Imagine and Party, they do quite well on this thing. So here you have an astronaut who's actually watering a tree on Mars with a spaceship in the background. And here is a portrait that has been created by Party, which was released by Google yesterday, of a raccoon painted by Rembrandt. It's quite impressive in this way of how you can generate this using generative models. And both of these paradigms in separate have certain pros and cons. So for example, generative modeling, which is what I call a white box here, they're data efficient because if you put a lot of inductive biases, a lot of physics of the problem or things that you know already into your model, you don't require as much data to train it because you have already put a lot of information in. They're interpretable too. So if you are modeling this using, for example, probabilistic graphical models or probabilistic programs, you can reason about why certain things are happening, why these predictions have been made. And they are, of course, better at generalization. You can incorporate causal structure and things like that. The black box models, on the other hand, are more flexible because you let the data speak, so they are less biased to human intuition. So you don't need to worry about human intuition of how the features are created. It's just the data that's letting the model learn about important features and making predictions. They are hugely accurate and fast. We know that from the huge successes of deep learning in some of the paradigms, but also they have this limited domain applicability, that how do you translate one to the other. And so a common thread of my research, at least for the past 3 years since I've been in Amsterdam, is to find ways to combine these two paradigms to create better learning and inference paradigms, basically. So how do we get them together? It's not, and I wouldn't claim that I'm the only one who's doing it. It's a broad field that everybody is pushing towards this, but that's how I think about research problems these days. And one way that we have been trying to do this is through incorporating symmetries and equivariances into the model. So symmetries are building blocks and were hugely important in physics. During the turn of the century, Maxwell was the one who first got to realize the symmetry between electricity and magnetism, which is to say that in the same equation applies to observers in different frames of reference. So for example, in this figure that I have of two different observers, one observer just sees electric field, but another observer who's going through with a velocity would see both an electric field and a magnetic field. It's just that the equations are still the same irrespective of what the frames of reference are. And this was later extended by Einstein when he realized the equality between gravity and acceleration, which is the same as how these two react given that the frame of reference changes. And more specifically, what I mean here by equivariance is the following. So I explain this with this picture. So let's say that I am interested in the task of object recognition. And so I have this egg-shaped sort of manifold on which there is a gecko. So either I can do is that I do some convolution, which is what I represent by K star, and I get some feature vector. Or alternatively, what I can do is I can apply a rotation to the egg, which is what I represent by phi, so that the gecko is now in a different position, and then I apply convolution. And equivariance is basically the closure of this diagram. That whether I take a convolution and then apply rotation, or I do a rotation and then apply convolution, I'd get the same result. And so at the high level, this is what I mean. This is what equivariance is, which is what I've written here in this equation too, that applying a function to the input that has been rotated by this matrix RG is the same as me applying the function directly to the input and then rotating it. And then you can think of it as, in some ways, equivariance sort of encapsulates symmetries. So you can think of in this Mona Lisa figure that maybe I have an eye detector and a lip detector and a nose detector and so on and so forth. And I can create these different capsules. And then this rotation symmetries are encapsulating this into parallel, that I can either rotate the features and then do the recognition, or I can rotate the image and then take the features and then do the recognition. So this is what I mean by equivariance here. And the advantage of equivariance is that, one, it leads to more efficient, data efficient models. It's easier to disentangle pose and presence as this image shows here. And it's also easier to detect patterns for deep nets. So in deep nets, a major thing that we do is to learn features that would be useful for a downstream task. And if you're incorporating these symmetries that are already present in your data, then you would be able to easily discern these patterns. And symmetries and equivariances are present in a huge amount of applications that are of interest to us. So for example, in molecular simulation, for example, you have all these 3D symmetries. So if you rotate a molecule in a 3D space, it would still retain all of its properties. In lattice gauge theory, you have symmetries with respect to permutations. So if you change the neighbors, if you permute the neighbors, you would still get the same energy function. I talked about object recognition, but social graphs is another one, that your connections with your set of social contexts doesn't change if you do this permutation invariance there. And in computational chemistry as well. So I'll talk about that later on in the talk. So ultimately, the kind of problems that we are interested in machine learning are three. First is that of model estimation or learning, which is that we are given certain data and we want to find an optimal model that can fit that data, which involves basically a minimization problem between the empirical distribution and my distribution that I'm interested in, and minimizing over the model itself. The next is that of inference or sampling, in which case now I'm given a model instead of data, and I want to generate samples from this model. And I can still write this problem as a minimization, but now the minimization are over the samples. And for completeness, there is a third problem, which is that of model checking, in which case you're given both the data and the model, and you want to check if these two are consistent or not. So in this talk, I'm more concerned about the first two, which is that of learning and inference, and show how we can incorporate symmetries there. And one thing, so the problem in machine learning is that, I mean, in the previous slide, I put the problem as a simple minimization problem. So it's like we can write this problem so neatly. What's the problem? The problem is that we in machine learning have data that comes from very diverse and esoteric domains. And therefore, we require models that can handle these different modalities. So we have really complex data, and therefore, to handle this complex data, we have created really complex models accordingly. And therefore, the problem of either sampling or learning or model checking is inherently difficult. And one of the things that I want to get across in this talk is that how I think about this is taking lessons from a diverse set of fields in machine learning and combining them together, or taking lessons from them to build better models. So this could be using control theory or RL, ideas from deep learning, problems in, that have been proposed as in the Schrodinger bridge problem or Stein's method, kernel methods, etc., and how we can combine all of these together or some of these together and build better models. So you'll see some part of it in the two models that I'll present today of how we use parts of these systems. So I'll now get to the crux of my talk. But I'll stop for a few seconds and see if there are any questions to the introductory part. Okay, so the problem that I first look at is that of sampling. So how I'd set up this problem is that, let's say I'm given a model in which I know that there are certain symmetries present. How can I efficiently sample from this distribution? So for example, in this picture, I have a Gaussian mixture model, which is 4 Gaussians, but you can see that each of the component is at 90 degrees to the previous one. So if I can take one mode and I rotated it 90 degrees repeatedly, I would get this kind of a figure. And so the symmetries that is present here is that of 90 to 90 degree rotations, which is to say that if I generate a sample from one of the modes and I rotate that sample by 90 degrees, I would get to a point that would still have the same value if I would put a density model on top of it, right? So then the question is, if I know beforehand that such symmetries are present in my in the model that is given to me, can I make efficient samplers? Can I use that information? So we do this through an algorithm which is called Stein variational gradient descent, which was proposed by Qian Liu and Dylan Wong in 2016. So Stein variational gradient descent, or SVGD for short, is a sampling algorithm which uses a particle optimized variational inference. So in here, what it really does is that you start off with a bunch of samples, so which are represented by these red dots. So let's say I start off with these n samples that are just generated by some distribution that I don't know. And it evolves these particles towards the correct distribution that I'm interested in, which is this distribution P, using this equation that I've written here. So it's very similar, the evolution of this equation is very similar to SSGD here. So now the crux in this evolution, so that these particles converge in a way that represents this distribution P, is to choose this velocity field, which is psi there. So how psi is chosen is that it maximally minimizes the KL divergence between QT. So QT here is the distribution that the particle represents at time t, and then the base distribution. So you want to choose this size so that this is maximum, like this is minimized. So this is a very hard problem. However, if the family F from which I can choose psi is restricted to an RKHS, so we don't need to worry about what an RKHS is. But if you put certain restrictions onto this family, then we can write it in analytical form. So the analytical form is that it has 2 terms. The first term, which I've represented in this red box, is the gradient of the kernel function, which defines this RKHS H. And that acts as a repulsive force between the particles. So the problem is that if you don't have a repulsive force, all the particles would collapse onto each other to a point that has high density. And that would give you the best sort of samples because everything has high density, but you don't want that, you want diversity. And this gradient of the kernel function gives you that repulsive force, which gives you diversity. The second term in green has a score function, which is the gradient of the log probability. And that acts as an attractive force towards high density regions. So it forces the particles to look for regions that have high densities. And therefore, through this mix of repulsive and attractive forces, the particles sort of evolve to sample from the correct distribution. So in this figure here that I have this 16 Gaussian mixtures that are aligned in this very nice way. And we start off with particles that are from a single Gaussian at the center. And then we let this evolution take place. And so you would see these particles get attracted, and now there will be repulsion, and then they move to different modes, and then there will again be repulsion and then attraction. So there's this thing that goes on between repulsion and attraction that lets the particles sort of go towards the modes, and then you get these samples that are coming from the correct distribution. So that's how SVGD works. The advantage of SVGD is, one, it's a non-parametric variational inference method, because we are just using some kernels here to define the method. And second, the sampler is deterministic. So there's nothing stochastic in here. Everything is deterministic. So in fact, if you want to learn a kernel, if you put a learnable kernel there, you can unroll the steps and then backprop through time and say that, okay, what is the best kernel that would be useful to do such evolution? So it's a deterministic sampler. All right, so that was SVGD. So how can we use SVGD to take advantage of incorporating such symmetries that are present? To set up the problem, let's say that my problem has symmetries with respect to this group G. So this G is the group that I'm interested in, through which my problem is symmetric to. So I can write the SVGD update that I've written up there into continuous time as an ODE. So it's basically, it's the same thing as dx by dt is equal to psi, which is just in continuous time that we are doing this. And the advantage of writing it in this way is that we can now lean into this theorem that I'm paraphrasing by Danilo Rezende and Jonas Kohler, who proposed this almost at the same time, is that if my initial density Q0, so whatever density that I'm choosing my initial particles from, are H invariant, and here H is a subgroup of G. So I'm interested in G invariants, but I can have Q0 be H invariant, and H is a subgroup. And psi, which is my velocity field, is G equivariant. So G is the group that I'm interested in for my sampling. Then the dynamical process that this ODE here represents will always give you densities through time that are G invariant. So it would always be G invariant, which is the group that I'm interested in. And now it's very interesting, because if I look at psi, the psi has two terms, as I said. The first is the gradient of the kernel, and the second is kernel multiplied by the score function. The score function is already invariant to G, because my probability density is G invariant, and the score function is just the gradient of that, which is a linear transformation. So it will already have the G invariant. So all I need to do for my sampler to be invariant is for my kernel function to be G equivariant. Because if my kernel function is G equivariant, the gradient is also G equivariant, and this whole velocity field then becomes G equivariant. And then I'm good. So my sampling steps would always lead to densities that are G invariant. And so let's see how this works in an example. So in this example, where I have this 90-degree, so symmetries with respect to 90-degree rotation, you can write the kernel, because we want the kernel to be G equivariant, as a sum over the orbits. So an orbit here would be that you take a point, you rotate it by 90 degree, you get another point, and you keep doing these 90-degree rotations until you get to the original point, and the set of points that you get is the orbit of that point. And so if you sum over the orbits of the point, so you take any kernel and then you sum over the orbits, the resulting kernel would be equivariant to this 90-degree rotation. So it's an inefficient way to do it, but it's a simple way to put it here. Like here, this would be like a summation of 16 terms. So in the animation, I'll show you. On the top row are the sampling results for an equivariant SVGD algorithm, and on the bottom is just an SVGD, is plain SVGD with no equivariance. So if I look at this picture, which when I first saw it, I thought that simple SVGD is doing much well in terms of sampling than eSVGD, where I have equivariance. Like the samples look all scattered out there, whereas here they are clustered together around the high density regions. But if I project these samples onto a single mode, because if I can get the single mode properly, I can get all the other modes by rotations, you see that eSVGD actually is doing quite well. in here in SVGD, all the samples have actually collapsed onto this high density regions, but they do not get as much diversity. Whereas there, it has captured the whole mode much more faithfully. And the reason is that through this kernel function, now SVGD is able to interact at a longer range, sort of is able to model these long range interactions. So what do I mean by that? If I take a point for an ESVGD algorithm, it applies a repulsive force, but it applies a repulsive force not just in its own neighbor, but through the orbit, it applies these repulsive forces throughout every point in its orbit. So it doesn't let any point get near to this original point in any place on this modes, which is why you get a lot more diversity. Whereas in SVGD, it only applies to its local neighborhood. So in all the other modes, the particles are still able to sort of occupy the same place because there are no long range interactions. And so here you have this sort of like this animation of how this evolves. And you see that in the lower part, it is coming to this high density regions, but there it is scattering a lot. And involving this is this invariance is also more robust in terms of log likelihood. So if this red line here is the ground truth of an average log likelihood of 1,000 samples. And if you plot the sampling procedure, like here we did 100 runs of this, you see that by incorporating invariance, you are much closer to your baseline than the regular one, which overshoots. And that's precisely because of this, this reason that it is not able to get this diversity in it. This problem becomes much more acute if you have a symmetric group that is continuous. So in here now I have a continuous symmetric group in the sense that it is continuous to rotations or symmetric to rotations. So if I want to sample from this distribution, if I can sample just the thickness of each ring, I have done my sampling part, because then I can rotate it through and I will get the samples throughout. And now you see in ESVGD, you can actually recover the thickness of the ring, but normal SVGD just collapses everything onto a single point, which makes sense because that's the highest density region. So it first has to cover all the high density regions before it even branches out. But then this shows that there is no diversity in the samples. And this problem is even more acute, even if you increase the number of samples. So in this figure, the dotted line again is the ground truth. The red plot is ESVGD. So you can see that ESVGD quickly converges to the exact log likelihood, and then it stays there. But for normal SVGD, which is the blue line, even with 32 times more samples than I have for SVGD, I'm not able to converge to the correct distribution or sample from the correct distribution. It's precisely because it's first just collapsing onto the high density regions and it's not able to incorporate that diversity. So this was sort of like a high level flavor of how to convert an SVGD into a sampler that incorporates inductive biases using kernels that are equivariant to incorporate these symmetries in sampling. So next I'll talk about how this translates into learning. So we learn energy-based models, and then we'll see how we can use a nice sampling scheme to learn them more efficiently. So an energy-based model is quite simply that you give some input to an energy network, and what it's outputting is what we call the energy function, which is the negative log likelihood of phi, which is my distribution here. And usually how we learn these energy functions is through contrastive divergence, which basically what it gives you is the gradient of the log likelihood. And so it has two terms. The first term is an expectation which is over the particles that are given to you. So these are some of the samples that are given to you and you want to learn the distribution over them. And the second term are the particles that you sample from your current estimate of the energy function. So that's what is the X minus that is coming from. So you have some estimate of your energy function and you have to sample from it. And then you can do this update to get the gradient. And basically what this contrastive divergence update is doing, which is well depicted in this animation by Sean Mishra and Jan LeCun, is that you have some data which is organized in this data manifold. And through this update, you're essentially lowering the energy on the data manifold and increasing the energy everywhere outside the data, wherever the data is present. And that is what exactly you want your model to do. So how do we convert these energy models to incorporate equivariances? So it's quite simple. all you have to do is that the energy network now needs to be a neural network that incorporates these symmetries, which is quite good because now we can lean into tremendous amount of research that has been done in developing these equivariant neural networks. So you can use either EN graph neural networks or steerable CNNs or other equivariant networks to incorporate such symmetries. But the other problem is that you also need to sample from these networks. And if the sampling itself is slow, then the training of the energy-based model is also slow. But now we can use ESVGD that I talked about earlier to improve the sampling process. Right? So one additional thing that you can do, which was proposed by people in Toronto a couple of years ago, was that you can view energy-based models as joint energy-based models. So basically, if you have not just unsupervised or unlabeled data, but if you have some labeled data too, you can incorporate that into the learning paradigm, which is that you have the maximum likelihood objective, but you add a supervised loss on top of it, which is basically the probability of the class given the data, right? And so you can put that into the same energy-based model, and by adding one more layer to your model, which gives you the class label, and then you can train it jointly using this objective. So you can do similar things here, that if you have data wherein some amount of it is unlabeled and some amount of it is labeled, you can use similar paradigms with energy network as an equivariant energy network. So I'll show some examples of how we did it for images and molecules next. So in this example, this was more a synthetic example. We took this fashion-eminence data and we rotated some of the images randomly by some degree. So here we incorporate a C4 invariant group, which is a group which is like invariant to 90-degree rotation. So we rotated images by 90 degrees, 180 degrees, or 270 degrees. And so we created a data set, and then we learned an energy-based model. And here the energy-based model was a steerable CNN. So it's a convolutional neural network that incorporates the symmetries to these 90 degrees rotation. And the last layer would also in the last layer, we also put some class label, how to handle class labels. So because we had the class label information. And we trained this using the ESVGD algorithm. So there we used the same sampling algorithm that was invariant to 90-degree rotations. So instead of the plots for how the generation worked, I look at the plot at accuracy because it shows something a little more interesting. So we compared, on the y-axis, we have accuracy in terms of classification, and the x-axis has the epochs in terms of training. And there are three curves in there. The blue curve is training an EBM that doesn't have any symmetry information. And the sampler that is used to train it also doesn't have any symmetries. So neither the sampler nor the energy-based model has any symmetries. The green curve is when the energy-based model has symmetries, but the sampler is a vanilla sampler. And the red curve is when both the sampler and the energy-based model have symmetries. And you can see that the red curve sort of converges or gets to the highest accuracy very quickly, just by the courtesy of it having a lot more information that's present in the data. So it's hardly surprising there. Whereas when the symmetry information is not present, the models do not do as well. They take a longer amount of time to converge. So we next extended this to molecular simulation. So in this case, we took a particular molecule. So this was an isomer. I think I forget the exact composition of this, but we took that isomer and we had a properties. We also had access to certain properties of this molecule. So these properties would involve, for example, van der Waals forces and certain energy functions that we knew about it. And so in this case, we modeled the energy function for this molecule as a graph neural network, just because you can represent molecules as these graphs. And we trained it in a similar paradigm. So we trained using ESVGD, given the data that we had. And once we had trained the model, we then simulated molecular structures based on them. So in the simulated molecules, what's interesting is that the original molecule had an aromatic ring structure, which is to say that it had these carbon rings, either 6 carbon rings or 5 carbon rings. And the simulated molecules all had this aromatic ring structure present in them, showing that it was able to sort of learn this compositional properties. In the other graph, what we have is sort of the density model that is come of either the carbon-carbon bond or the carbon-oxygen bond, just to compare how it compares to the data that we were given and what the simulated molecules look like. So there, the samples do not look as good in terms of how the true samples were, but still the peaks of both the simulated molecules and the true molecules sort of coincide in this field. In a subsequent work that came out from Amsterdam by Emil Hoekboom and Victor Sartoris, they actually improved these results to show that these actually match exactly well with the data that we had at hand. Another application of this work is that you're given a molecule which is present in one stable state, and you want to find out what are the other stable states that the molecule has. So that is what I show on this, in this case, the right-hand corner, where I have vanilla EBM and equivariant EBM. So what we had was that we took one of the metastable states of the molecules and trained our energy network on that using equivariance. And then we simulated newer molecules to see whether we can find out other metastable states that are equivariant to the one that we trained on. And you can see that in equivariant EBM, we recover all 5 different metastable states. So these are all 5 different configurations that are equivariant to each other. Whereas a simple EBM is not able to do it. It was trained on those molecules and it only stays with those molecules. It doesn't sort of generalize to these other modes that are present. This is also sort of just to reinforce that incorporating this symmetry information goes a long way in terms of recovering these modes that have information in these domains. And here I have just a small plugin of a recent work by, again, Emil Hoekboom, Victor Garcia Sartoris, Max Welling, and co-authors, where they use diffusion models to generate novel molecules. So they do a similar kind of thing, that they turn a diffusion-based model using this EN graph neural network to incorporate symmetries, and then they simulate sort of novel protein structures. Yeah.
Do the different configurations of molecules
Mhm.
appear at a relative frequency similar to the actual chemical if they like synthesize it in the lab? Do the different like configurations appear there in the same frequency as the model produces when you sample from?
Right. So I mean, if we learn the correct energy model, then it would have the same. It should have the same frequency. Otherwise, it would not get the modes. It's not getting the modes right. And so in my previous slide, at least so this you can sort of view it as a proxy for the frequency that you're talking about. And here it's not doing as well because there's a disparity between what the true distribution looks like and what the samples are giving. But the improved model that I'm talking about does recover this kind of sort of the frequency. Yeah. So yeah, that was like one part of what I wanted to talk about. I am running out of time, but I'm very interested about the second part as well, which is sampling rare transition paths. So this is a problem in which you are given 2 stable states of a molecule, and you want to find the transition path that leads from one state to the other. So more formally, what it means is that you have one state, which is X0, which I call the initial stable state, and XF, which is the final stable state. And then you have what I've shown here as this energy landscape, where X0 and XF are at lower energies represented by blue regions. And you want to transition from one state to the other. And you want to find a path that goes over this, that takes you from one state to the other. The problem is that these 2 states are often separated by a free energy barrier, which is what I've represented by this, which is represented here by this green sort of barrier here, right? So you have to go over this free energy barrier to transition one state to the other. And the problem of sampling rare transition paths is to find the path of least work in this case, which is to say that you want to go over the energy barrier at its lowest point because you don't want to do extra work that can transform X0 to XF. Interestingly, this problem was first, I mean, I am putting it in terms of molecules, but in its original form, it was proposed by Schrödinger back in 1930s for quantum physics. And then there has been a lot of work that has been done theoretically in this. So it's called a Schrödinger bridge problem. And this has a lot of applications. For example, in chemical reactions, you can view the initial stable state and final stable state as your reactants and products. And oftentimes in chemical reactions, you have to apply forces or energy from the outside to drive the chemical reaction. And so that is equivalent to crossing over this free energy barrier. Or conformational changes, which is how a protein sort of folds, is also another example of this. Or even phase transitions. So going from a solid to a liquid, or a liquid to a gas, or the other way around, or crystallizations, are all examples of converting one stable state to the other. So usually how people go about solving this problem is that you model the dynamics of the system. So here you can model this as a stochastic, as an SDE, which I've written here, which has, one is the drifter, which is what I've represented by F, and then the Brownian motion, which renders stochasticity to the evolution process. So one way to sample is that you just run this SDE, where X represents your molecule. And if you run it for a long enough time, it would get to the final configuration just because this is how the evolution happens. However, there are problems with this kind of approach. The first is that it's very slow. And the reason is obvious, that because you have to cross over a free energy barrier, if you're not drawing any external force, it's similar to saying that you have to go through a region that has really low probability, and the sampling algorithm would not sort of try to bypass that region. So another way that people have tried to tackle this problem is to recognize what the control variables of the problem. So here you can think of control variables as sort of important features that, if you change those features, would give you the resultant sort of this transition path. So in normal machine learning parlance, I would call this as a lower dimensional subspace of features that are important. The problem with identifying these control variables is that identification of this is actually harder than the problem of sampling rare transition paths. So for some problems, we do know what the control variables are, but in general, finding out these control variables is a very hard problem. And thirdly, we are also interested in the characteristics of the path that we are going to take. So we want a certain amount of control over what path we are sampling. And if we just run this molecular dynamic process, we lose this control. So in a paper that is going to be released, I think so in a couple of days, we will release it. What we did is the following. So we took the molecule, and instead of letting it evolve over time on its own, we added extra forces to each of the atoms. So instead of learning the control variables, we say that we will just add forces to each of the atoms, and we will apply these forces and see how we can learn these forces in an optimum way that it will help us to transition over the free energy barrier. So what it means in terms of that SDE that I showed you earlier is that we add this force UXC to the term. So earlier we didn't have UXC, we just had we had all the other terms. So we have added this control basically to our problem. And the problem now is, how do we learn this UXT? However, so the first thing to notice in this model is that now we are applying forces to these atoms, and these forces would change the corresponding positions. But that doesn't align well with Newtonian dynamics that the molecules would follow. So how technically this should happen is that you apply forces to the atoms. The forces give each of these atoms certain velocity, and then the velocity changes the position of the molecule. So you want to incorporate that Newtonian dynamics or these second order dynamics into your system. So to incorporate that, we instead consider evolution on an augmented space. So now the augmented space consists of R and V, where R is the position and V is the velocity of the atom. And now you can see that the control, which is U, is only acting on the velocity, just because the top part of my G matrix is 0. So what it's doing is that the control changes the velocity, and then the velocity changes the position. And so in this way, you can incorporate the second order dynamics into the system. And you can then model this UXT to be some deep neural network. And if you want to incorporate symmetries, you can have that neural network to be an equivariant neural network, which either directly predicts the force. So it either gives you the force directly, or it can be an energy network. And then the force is just the gradient of the neural network. So you can either do force prediction or energy prediction. So let's see how, and so as I said earlier, that this is equivalent to a Schrödinger bridge problem. So here I'll show you an animation of how such a network, such a policy network, which is learned using stochastic optimal control, works for this molecule, which is called alanine dipeptide. So this is a very well-studied molecule in computational chemistry. It has two control variables that are known already, which are represented by phi and psi. But in our method, we do not need control variables, but we'd use that as a proxy to judge how good our method is doing. And so in the plots that I have, so I have shown the positions of both the final and the initial configuration through these arrows on the energy surface. And on the right-hand side, you will see how the molecule is sort of evolving over time. So how the molecule conformation changes are happening. And at the bottom part, I'm plotting the potential energy. And we'll see how the potential energy would rise initially, because we'll go over a free energy barrier and then subsequently sort of decline to get to the metastable state. So you see that initially this energy sort of is rising, and that is sort of tracking the progress of the evolution above. And so the path is sort of, it's going around lower energy regions. So it's avoiding these yellowish regions as much as it can. And from D, it will now converge to the final configuration there. And if you, like in this slide, I've not shown, but interestingly, even though we have applied forces to each of the atoms, the policy that we have learned is learned in like it automatically detects what the control variables are, so that the major changes that are happening to the conformations of the molecule are only happening along these angles that are these control variables. So that was very interesting, because it's an unconstrained model, but it still learns to only apply forces that would lead to this change. So this is a smaller molecule. I'll show a larger molecule too, but first I'll show more quantitative results. So in this table, so I'll parse all of these terms that we have here. The red block is the control the model with control that we are learning, and we have two ways of determining the control. Either we predict the force or we predict the energy. And MD is molecular dynamics simulation. And we do molecular dynamics simulation either with a fixed time scale, that is, we only run the thing for 500 femtoseconds, or without a fixed time scale, in which case we just let it run until it converges to the correct position. And we compare the two methods on three metrics. EPD is the expected pairwise distance, which is to say that your model takes you to certain configuration, and what is the distance between this configuration and the final configuration that you're interested in. THP is the total hit percentage, which is that how many times you are around the neighborhood of the final configuration that you're interested in. And ETP is the energy transition point, which is that at what highest point in the path that you made the transition over the free energy barrier. So you want to do it at the lowest point there. So lower is better there. Total hit percentage, of course, has to be higher, and the expected pairwise distance has to be lower. So along all these three metrics, both the force prediction and energy prediction are doing way better than molecular simulation. So for example, in terms of where it crosses over the free energy barrier, you can see that for molecular simulation, it's either around 500 or 1000 kilojoules per molecule, whereas the other ones are doing at 0.68, which is a huge amount of difference of where it's crossing over. But what's interesting is that for molecular dynamics without a fixed time scale, it takes about 34,000 or 48,000 femtoseconds to reach to the target configuration. And compared to that, when you apply a control to your problem, you can reach there in 500 femtoseconds. And that's just because you can decide in how much time you want to converge there, and then you can learn your control accordingly. So this is just a demonstration of how it leads to really real benefits in these problems. And so in the next case, we extended it to a larger molecule, which is what we call Proliproline Helix. It's a helix-shaped protein. And here too, the control variables are known beforehand. So we know what the control variables are. There are three control variables. But interestingly, in its folding process, there is only one control variable that is important. The other two sort of remain the same. And so in this graph that I have here at the bottom, we have shown three control variables, which are represented by omega, phi, and psi. But omega is the only one that's important. And we'll see how the evolution happens there, as well as the energy. So you see at the first point where I've drawn this dashed line is where the red sort of drops to by a large margin. And that is where a huge change in that control variable has happened. And then secondly, again happens in that blue curve as well. So those are the 2 points where the molecule changes its structure drastically to get to the final configuration. And similar results also can be seen for Chignolin. So this is a very interesting example, because Chignolin is an artificial protein that was created to study the protein folding mechanism. However, a lot of research has been done on it because the control variables are not known. So earlier sampling strategies were not able to target this protein structure as effectively. And so because our method does not require learning these control variables, we were able to sort of work with this molecule and sort of simulate its folding process here. And so you can see again in the pairwise distance graph, which is the first graph that I show, that over time it converges to the true final state that we are interested in. Okay, so I have a couple of slides just to quickly summarize. So in the initial part, I talked about equivariant sampling. And there I talked first about SVGD, which is a Stein variational gradient descent algorithm for faster, more robust and efficient sampling when we know what symmetries are present. However, a caveat with using SVGD is that it's quite sensitive to kernel choice and its hyperparameters. So you have to do a lot of work with what kernels you're using, how you're parameter or how you're choosing the hyperparameters and so on and so forth for it to work well. Then we extended the use of this sampling paradigm to train equivariant joint energy models and by incorporating equivariant information that was present in the data. But as is the case with training any energy-based model, if the sampling procedure is not efficient, or you don't have something that samples fast, you require really long chains because you want to converge to the correct distribution before you do your update step. And that happens in this case too. It's much better than not incorporating equivariant information, but still it doesn't mean that the training of energy-based models has become suddenly very simple. It still requires certainty. And then I talked about a little bit about some of these applications of these models in molecular simulation, many-body systems, etc. Before I'll conclude, I started with this slide of sort of trying to get or take lessons from these different branches and incorporating them to build better, more flexible generative models. And I think that there's still the way to go. We are seeing a lot of it in present works. For example, the diffusions are using a lot of work from not only dynamical systems, but there are diffusion models that also incorporate equivariance, which I talked about. I think so that would still, like, a lot of work is being done, and I'm very excited that that a lot of exciting work is still being done in this. And the reason is also that this just does not lead to better models, but I'm very excited about the many applications of this in the next sort of set of core disruptive AI applications. So one of them that I'm very interested in is molecular biology, computational chemistry, and material sciences. I was reading a report, I think so now it is a few months ago, which said that in industrial processes, 70% of the energy that is lost due to friction. And in tribology, an active area of research is how do you build better lubricants so that you minimize this loss of energy that is happening in industrial processes. And that problem, you can actually formulate it as not only as a discrete sampling problem, but also as an RL problem, because the building better lubricants is basically, if I understand the limited literature that I've read, is combining different oils to get desired properties for an industrial process. And so a lot of work is actually being done in lubricant and catalyst design using machine learning and tribology, but also in health sector. So building better vaccines, better medicines, sustainable solutions so in that there is a lot more push of using machine learning to build better materials which are more sustainable and do not harm the environment, and energy sector. So I was talking with Pascal today in the morning that one of the things that I have in mind is how do we convert solar energy into something that is easily transported. And one way to do that is you convert it into hydrogen energy. And that basically involves a reaction of converting water or decomposing water into hydrogen and oxygen, which requires a lot of energy, and you don't want to waste that. So it requires better catalysts that can drive these reactions forward. And I'm very excited to see a lot of groups in machine learning around the world are looking into these problems these days. But not just these problems that we as society are facing as large, but also in areas of chip design, circuit optimization, and compiler and EDA, that there are lots of applications for generative models, for sampling paradigms that incorporate these equivariance information. So for example, in logic circuit optimization, you can formulate the problem either as an RL problem, again, because you want to minimize the size of the circuit, but you want to maximize how quickly it evaluates things. And there is generally a trade-off. And so you have these equivariant transformations there that you can apply to a circuit, which would either reduce its area or increase its throughput. And then you have to find a balance. So it's an interesting space. And lastly, it also has many fundamental problems that you can tackle using this. So for example, Bayesian quantized neural networks, so that you can then do federated learning. So Pascal and his students were talking about this today. And I was talking about the communication. If you're communicating models, it requires huge bandwidth. So one way to do that is that instead of using, you can use quantized neural networks and reduce the amount of bandwidth that you're using in terms of communication across devices. And then how can you use these to do a Bayesian quantized neural networks? But also, like, for example, the first project I started with Pascal as a PhD student was distributed and online learning for Bayesian models. And I'm still interested in those problems, but how do you do it using a particle-based variational inference method that I talked about, so that you can do this. So that's mostly it that I wanted to talk about today. It's a real honor to be here, to be talking with you, and I look forward to your questions and discussion. Yeah, thank you.
Yeah. Also, I do have some questions. So when you talk about applying forces to, I guess, find an optimal path to transform a molecule.
Right.
So I'm not familiar very much with molecular biology, but here, what does that correspond to? It's the idea that there are ways in which we can apply forces
right
to engineer the type of molecules we want. Or would that correspond more to what happens in nature, and molecules would naturally stabilize in some state by just reacting to existing forces?
Right. So in this case, what it would mean is that, so if I just go back to that part. So here, what it really would mean is, when I say apply forces, is that you really put it in a solvent. So it's trying, like, you put the molecule in a solvent, and the solvent is sort of acting on the molecule. So these forces that I'm applying on these atoms are coming from the solvent in which we would put the molecule. And the idea here is that the objective is that if, like, this energy landscape that I've defined here, that I show here, is basically you have different configurations of your molecule, and different configurations of the molecule correspond to different energy patterns, which is what I've represented here. And the molecule, the initial and final state, are two stable states of the molecule. And we are interested in how do we transition from one to, so you can think of it as, I want to crystallize a molecule. So in that case, I know what the final state would be, and I know what the initial state is, but I want to drive that reaction so that it actually crystallizes. But now I want to do it in a way that reduces or minimizes the amount of work or energy that I'm providing from outside to do this. And the way of doing it is either you use a catalyst or you use some supporting sort of things to drive that thing forward. And that supporting thing would be what would encapsulate this outer forces that you're applying.
Okay. Yeah. So I guess I have to know from the perspective of a catalyst that yes, we can design catalysts that will have some properties and
right
to certain reactions that will follow a certain path and have a certain energy there. But then in that space, the trouble is that we don't know what the effect of different catalysts is going to be.
Right.
And the work you presented, it sounded like, we could just apply forces.
Right.
And then they'll have whatever effect we wish them to have. So I guess I'm just missing how we manage to actually apply.
Right. So that is that is the next step in this. Of like first is determining like the forces that would lead to this change, and the next step is, okay, now that we know these forces, how do we convert it in practice to lead to make this change? Okay. And that from what I understand with my talks with people who are well versed in computational chemistry is around designing solvents that would provide this kind of these kind of forces. So you have the molecules and solvents, and the solvents are basically sort of reacting with these atoms, and they would push. And that is my understanding currently.
Okay, I see. So basically, we're trying to find a path without worrying about how we're going to really follow that path.
Right.
And then after that, then it's okay, the path exists. So now we'll figure out solvents, catalysts, whatever
that would help. I think there's something on chat, but I can't open the chat. So if somebody else is on Zoom and can tell me, I'm sorry. In the meantime, you can.
So we could use a solvent to do it. Are we at a point with like our protein model, like we could engineer an enzyme or something to apply desirable forces to catalyze?
It's a good question. I admit that my knowledge in that space is very limited. So I'm not aware if there are enzymes already that apply that kind of forces. My guess is people are working on that, or that would be like when you go into this idea of designing newer molecules, it revolves around either getting catalysts or these supporting molecules that would help drive a reaction.
Right.
But I don't know if they already exist or not.
That would be a really interesting thing, because that's sort of how biology, hacks these problems.
Right.
It's a big molecule that just forces other molecules into the shape it wants.
Right.
So we could use, an AlphaFold sort of model to make things that do. That's.
I mean, my hunch is that yes, people are doing this kind of work, because there's a lot of work. For example, I was talking about converting solar energy into hydrogen energy, which requires catalysts. Right now, the enzymes that you're talking about would also act as some sort of a catalyst here, in the sense. So there is a broad range of work that's happening there. But I'm not aware if there is an enzyme already present that would do this.
Okay. So basically, there were no questions really, but just can you
repeat the question? Oh, I see. So the one that I was answering right now was just, if I'll paraphrase it, is they were asking if there were already some existing enzymes which would apply these forces that I was talking about. And Pascal was asking a precursor to that question, which was that now that we know that we have to apply these forces, how does that translate in practice? How do we apply these forces now in practice to convert the molecules? And my answer to that was that it is usually done through using certain solvents, but that is also the next step in the project of, now that we can determine this least path, how does this translate in practice?
I have a question from the call. You can hear me?
Yeah, I can hear you. Please go ahead.
Hi, great. Yeah, it's Mark Coley here at EC. Great talk with lots to think about. I'm not even sure I got to process it all, but really cool things. You mentioned reinforcement learning a bit at the end, I think. I think some of your control approaches kind of implicitly do some of that like almost in the same way, but I don't know if it's actually reinforcement learning in that sense or optimal control. And I'm just curious about how that relates, but also about how you could apply these things where the groups of the equivariances aren't in something that's like a physical system, but in more of a state value action space. I don't know. Have you seen things like that?
Right. Yeah. So for the first part, at least in this work where we were learning these forces, so here the formulation is more along the lines of stochastic optimal control. So in particular, we use sort of path integral stochastic optimal control to solve this. And so this reference that I have at the bottom, which is now not really visible, but basically this is a work done by Bert Koppen. He has done a huge amount of work in this area on how to build algorithms that you can solve these problems in closed form and get algorithms. So we use that algorithm here. So this was more a stochastic optimal control formula. With respect to the other part that you mentioned of how can we incorporate now these equivariant information in this state action space here. So in this case, how we have also not done this for this work particularly, but if we were, what we have been doing currently is that we are modeling this control that we are using because this is deep network. So now we are using an equivariant deep network instead. And that, if you look at the equation that we are using here, is all that we require to incorporate these symmetries, because the positions of the molecules are these x, so that is what we require them to be equivariant to. The drift term, which has this gradient of the potential energy, this comes from simulations. And that already also has this equivariant information, because the space that we have of molecules, the energy that is being defined is equivariant to all these 3D transformations. So this term also has the symmetries built in. And so where we require the symmetries to be present is in the control that we're applying from outside. And if you're using a neural network, then we want it to be an appropriate equivariant neural network. And so we are doing those experiments right now. So I don't have results for those experiments. And at least in here, that's how we are incorporating this information. But more generally, for your question on like for reinforcement learning in general, how can we incorporate this for state action pairs? I think I can offline send you a link. There was a work from Max Welling's lab itself. I think Elise van der Poel was doing that work that was presented at last year's NeurIPS, where they did, I think so, I think they called it homeomorphic MDPs, which were incorporating these symmetry informations for reinforcement learning, where you had these state action pairs.
Okay, great.
Does that answer your question?
Yeah, it starts to. Yeah, it's just an idea filling out there. So yeah, maybe I'll send you an email.
Thank you. Perfect.
Great, thanks.
Pascal.
So maybe as a follow-up for reinforcement learning, I can see how we can formulate the problem as having like a start state, a goal state,
Right.
and then we can have some more that correspond to like the energy consumption that would be needed. And then would it be fair to say that now this is like a continuous control problem because we don't have discrete time steps,
right.
So we're applying forces continuously.
Yes, yes.
And then so most of the work in reinforcement learning, in fact, is with discrete time, but this would require a continuous time version.
So like the formulation that we had wasn't continuous time, but we did discretize space. So in here, for example, for this molecule that we did, how we did was that we took a certain amount of steps for at each 10 femtoseconds, and then we would, so we discretized it accordingly, and then we would interpolate between those discretizations. And that was just to make things more simple in terms of setting things up or implementing them. But how we formalize the problems and everything, it can be done in continuous time. So like in particular, like I didn't include this slide, but really like this is, I mean, because it has a whole lot of this jargon that I didn't want to go through, but it's basically what we are doing is that we define some cost function, and then we are optimizing it dynamically over time. Like we unroll the whole thing and then go back in time and say, okay, what is the right amount of control to be applied at each time step? And that's how you sort of optimize and learn the whole energy network. So for example, the thing that I've written here, C, is saying that it's the cost for taking a sequence of actions when you start from x naught at time t naught, and your control goes from t naught to tf. And it consists of like two terms there. The R is the deterministic cost of taking an action at a particular point, and then phi is the cost of ending at a certain state. And then you're integrating it through time, and then the expectation is over the stochasticity, which is the stochasticity of the Brownian motion. And then the whole So here it's not visible too well, but I can send you these links of where the complete algorithm of how do you optimize this cost happens. But then the application is through discretization. Oh, sorry. So for people who are joining hybrid, Pascal was just asking that, like here, because I was talking about control, is the problem set up in continuous time, whereas things in reinforcement learning are more discrete time. So how things were set up here? And my answer to that was that the formulation was completely in continuous time, but for ease of implementation, we did discretize, and then the final algorithm was in discrete time.
Hi, I just had a question.
Yeah, please go ahead.
Yeah, thanks for the talk. So, in the problem of sampling from a symmetric probability distribution, what is the advantage to directly sampling from the density as it exists versus first restricting the density to a subset and then sampling from that restricted density? So I guess in the case of the C4 Gaussians, we know that the overall density is just one Gaussian that's been rotated 4 times. So why not just restrict it to the one single mode distribution and then sample from that?
Yeah, so actually that's exactly what's happening when you incorporate symmetries. So as soon as you incorporate symmetries, you have turned your problem from sampling from these 4 Gaussians to just sampling from one of the modes. So you are working in what we called a factorized space. So that's exactly that's happening here. The reason that I didn't, like in the pictures that I've shown, that I didn't just show one mode and then sample from that, is that oftentimes in problems, you do not know what that mode also looks like, right? So you cannot factorize it easily to that one mode. So for example, for 4 Gaussians, it's easy, but for any real world application that you're interested in, you do not know beforehand what a factorized distribution looks like. So what is an easier way to do is that the sampler incorporates that symmetries and then you sample from the original space. But implicitly, such a sampling paradigm is sampling in that factorized space, which is in this case, just sampling this one Gaussian here, which is this mode. So does that answer your question?
Yeah, I see. So it automatically is doing that.
Exactly. Yeah.
So in this, I want to ask, so would the expert need to specify ahead of time what he or she thinks are the symmetries, equivariants that the model needs to explore, or is there even a way to allow them all to discover them and explore them? Right.
So yeah, that's a good question. I've been thinking about it. So in this case, we need to know beforehand. And I think, I mean, it's a difficult problem to discover symmetries on the fly. There is a certain amount of work that's happening there for simpler groups. But I think it's a difficult problem. I think one way to how I have been thinking about, doing it is taking advantage of Noether's theorem from physics, which says that every symmetry group has a corresponding, like if there is symmetry present, then there is something that is conserved. So some energy or something that is conserved. So conservation and symmetries are sort of like an if and only condition. So they go both ways. So you can either incorporate symmetries by having such symmetries, or you can say that there is a corresponding conservation law and you can model that conservation law, and that would implicitly model symmetries that are present. And I think that would be one way to learn symmetries, that you make your networks learn in a way that they're conserving some quantity. And just by courtesy of them conserving some quantity, if you're learning it in big data, they would implicitly model those symmetries that are present. Now, even finding out what the conserved quantity would be a bit difficult, but I think that might be like a more natural way of discovering symmetries rather than changing functions. So, but that is my hunch. The kind of work that people have done, they have tried to model symmetries by, like, so for example, generalizing convolutional neural networks. So saying that convolutional neural networks are a specific form of parametric functions. And now they're saying, can we extend this parametric family to a larger family and learn the parameters so that they incorporate different kinds of symmetries? So there has been some work around that too.
So if not, let's thank you again.
Thank you very much.